We are now starting off with another technique or another idea as regards integration 2, which we call the function and its derivative, or recognizing a function and derivative. To integrate a function in this case, you must have differentiation ideas in mind, and the situations of a kind are, for example, you're told to integrate x squared and multiplied by the square root of 3x cubed plus say 1 dx, and outside here I may add a 9, maybe for the first illustration. When you look keenly to the quantity under the square root, when you look keenly at this quantity, you notice that the expression 3x cubed plus 1, when you differentiate it, you actually get the quantity outside. So when someone lets say you to be 3x cubed plus 1 and differentiates normally du by dx, so now when you drop the power as usual, 3 hits the 3 to give us 9, x reduce that 3 by 1 to get a square. The derivative of 1, remember the derivative of 1 is 0, so we get 9x squared. Keenly look at the answer I've got, compare it with the term outside the root. So you notice that when you differentiate the expression inside the root, when you differentiate the expression inside the root, you get the term outside. You get the term outside. That's what we call recognizing. The ability to see that when I differentiate the term inside the root, I get something similar to the expression outside. This sample I've given at the beginning may give you the exact derivative, but sometimes the constants may not be as expected. For example, when you look at the derivative of this situation, when someone is to let, normally one would let u to be the square root of 2x squared minus 1, for example, squares both sides to get 2x squared minus 1. Now in this situation, you're preparing to differentiate, but you expect to get x as the derivative. On differentiating, we get 2u du equal to 4x dx. The derivative of 1 is 0. Dividing both sides by 2 here, u du is equal to 2x dx. Even when I go on to reduce, this time it's not the same. I get x, but I get 2x, but in the function I have x, it doesn't have the 2. That's not the end. Our interest should be which variable is in question. The variable is x, it is to power 1, and the one I'm getting still is also to power 1. That keeps you still safe. You have recognized the function and its derivative. When you differentiate this, you get x. The constant before it may not matter, but the ability to notice that when I differentiate, the powers are the same with what I expect to be the derivative. Let's look at some examples. In our examples under the second technique in our series, we want to look at a case when the power whose derivative we see outside the function is here, its power is an integer, when it has a fraction power, and when it's a ratio, in other words, it's a denominator whose derivative is the numerator. With part A in our solutions, let's start with part A. Let's start with part A of number 1, where we are integrating x into x squared plus 1 all squared dx. So I'll let u be that function whose derivative I note. So when I look keenly, I see x squared. When I differentiate x squared, I get 2x. But outside here I have x. However much the 2 is missing before it to be the derivative of this function, I should not hesitate to differentiate. That process is carried out in 2 ways. One, a candidate will say let be x squared plus 1. When it's an integer, ignore it, just let the expression inside. Du by dx is equal to 2x. The derivative of 1 is 0. In that case, you will notice that when you cross multiply, you get 2x dx as du. But there is no 2 before. So make x dx the subject. It will be du over 2. Rearrange by writing this as x into x squared plus 1 all squared dx, which is equal to the integral of x squared plus 1 all squared times x dx, which now can be put down as which can be put down as the integral of this quantity is what I've let to be u, but it is squared times my x dx is here, my x dx is du over 2. That leaves me with a half the integral of u squared du. And when you try to integrate that one, easily you will have this as a half into u cubed over 3 plus a constant, which is 1 over 6. Where we have u, we replace our x squared plus 1. And that is the solution to part A. Part B, number one, part B, we are integrating 2x, the square root of x squared plus a dx. It's important to mention that a is a constant. A is a constant. You may be told that a is a constant such that you find the differentiation process easy. Now, back to the recognition. Remember, we want to first of all see a function and derivative before we start the process of integrating. Now, when you look keenly, when I differentiate x squared, I get 2x. Now, this is 1 in a million. It may be one of those few questions that the derivative is prepared clearly as it is expected. So when you let, for example, t to be the square root of x squared plus a, square both sides, t squared is x squared plus a, differentiate 2t dt is equal to 2x dx. This time around, the quantity I get, 2x as the derivative, is as it is expected in the question. So when answering this time round, you will say the integral by preparation of 2x, the square root of x squared plus a dx becomes, you will now write it as you have differentiated. Bring that quantity under the root first, and then followed by the 2x dx. This is the first time I'm doing this. When I do such a preparation, I'm organizing my equation for substitution, such that as I change the variable, everything is suited or ready for the new variable. So this quantity, we let it to be t, and the 2x dx is our 2t dt. So when you substitute in this, let's do the substitution down here. When you substitute in this, square root is t, that whole quantity under the root is t, multiplied by that whole quantity 2x dx is 2t dt. It is 2t dt. So right now what you have, you can put it down as 2t squared dt. And when you integrate, it becomes 2t cubed out of 3 plus a constant. Recall from your previous steps that t was known. That t was known as x squared plus a all power half. The square root of x squared plus a implies that. So when you substitute it here, your integral finally will be 2 out of 3 into where we have t, I'm putting x squared plus a, but it is cubed. Cube the other quantity, you get 3 out of 2 plus a constant as the solution. To part B of number 1. And lastly, in our discussion under this section, number 2, where we are told to show that this integral with the limits from 0 to 1 is equal to a third the natural log of 2. Natural log, this is normally implied as the log to base e of 2. So natural log of 2 is log to base e. Natural logarithm is a logarithm whose base is a natural number e. So from the left hand side, under number 2, from the left hand side, we want to carry on from 0 to 1 of x squared under x cubed plus 1 dx. So at that point, you let u be x cubed plus 1. Differentiate, du is equal to 3x squared dx, derivative of 1 being 0, don't forget. And at that point, what I have in the numerator, maybe to mention, what I have in the numerator is x squared dx. What I have here as x squared dx is attached to a 3. So preferably one can divide both sides by 3 and you have a third du as x squared dx. So in that order, then let's substitute for integrating. However, maybe to mention, we should not do anything before the limits are changed to the new variable. Our variable is u, so we should change the limits from x to u. So when you changing limits, we normally say that we have had our variable as x and we want to change it to u. The limits have been 0 to 1. So u is x cubed plus 1. U is x cubed plus 1. When you substitute 0 here, you will get u as 1. Substitute a 1 here, you will get u as 2. So our original integral, which was from 0 to 1 of x squared dx over x cubed plus 1 will be the integral from what has been 0 is now 1. What is 1 is 2. X squared dx, we have it here. X squared dx, we have it here as a third du. Then the quantity x cubed plus 1 is what we abbreviated as u. So resultantly, I have a quantity a third, the integral from 1 to 2 of 1 over u du. Now, I want us to notice that what we have is another function and derivative, 1 over u. And these are cases where we have the integral of, when the denominator is the function and the numerator is its derivative with respect to x. Such integrals, to integrate that thing, we normally say is the natural log of the denominator, f of x plus c, without limits. So with the limits, you evaluate. Now when I differentiate u with respect to u, I get 1. Directly, that integral will be a third, the natural log of the denominator. Careful, compare the two. Natural log of the denominator from 1 to 2. And that gives me a third, the natural log of, insert limits, natural log of 2 minus natural log of 1. Natural log of 1, remember, any logarithm of 1 to any base gives you 0. What I power to a to get 1 is 0. So this is a 0. I remain with a third natural log of 2, which is exactly similar to the right hand side, which is exactly similar to the right hand side as given in the question. Now, I'm going to just add on your screen trial questions about the function and derivative, and in our next episode we will be discussing another technique of integration. And I would thank you for following us in these episodes. Please subscribe to our YouTube channel in the names of Lawrence Senyondo, and for any query reach us on that WhatsApp number on your screen, and don't forget to share with your friends. Thanks for watching.